Okay, can you hear me at the back? You all okay? Good. How many people here have used wide gamut color? Hands up. None. How many people know what it is? You will in 45 minutes. Okay, good. So this is me, just to prove that it's me. I'm a technical director at the World Wide Web Consortium, but the most relevant thing here is that I'm the co-editor of CSS Color 3, 4, and 5. Also the W3C liaison to ICC, which stands for International Color Consortium, not International Criminal Court, in case you were wondering. So what are we going to do today? First of all, color science is really, really complicated, so I'm going to explain it in 3 minutes. Then I'll explain why you're in prison. Then I'll explain how to get out of it and what more stuff you can do. And then the big question, can you actually use any of this stuff? And if we have time, a little bit about high dynamic range, which is the next big thing after wide gamut color. So, what is color? Could any of you define what color is? What does it mean? I'm not asking you to, I'm just wanting you to have this feel of an existential dread and hope that I will explain it. So, color science is super complicated. It involves measurements on human eyes and color matching experiments and all sorts of stuff. There's a lot being written about it, and most people know two things about color science. One, it's super complicated, and two, nobody needs to know that stuff. But don't worry, we're going to look about what you need for a color model. We're going to develop one from scratch on stage. So, first thing you need to know is light and dark. Is a color light? Is it dark? Is it in the middle? So there we are. There's a color scale. This is actually luminance, which is a measured quantity. You can get instruments that measure luminance. Is there a problem with this scale? Like, the midpoint is away over there. That's just no use whatsoever. Our eyes don't see light that way. You can measure it that way, but that doesn't tell us what we see as equal brightness. Here's a better one. This is CIE lightness. White is there, black is there, mid-gray is right in the middle. All the steps seem evenly spaced. This is a much better start. Okay, now we've got light and dark. The next thing we need, colors. Now, we're going to do an experiment. I want you to look at the black dot in the middle. Resist the temptation to let your eyes wander around. Just look at that black dot. You'll need at least 30 seconds. Just keep looking. It'll be worth it, really. And what do you see? Okay, the color you're seeing is not there. The color you're seeing is in your eyes. That is the opponent color. Every color has an opponent color that your eyes will see as its exact opposite. No color can be both of those simultaneously. It has to be one or the other. If it's both, it's gray. So, that's one opponent axis. Let's do another one. Same deal, black dot in the middle. Keep your eyes fixed there around 30 seconds. 15. Doing well. I know it's hard not to let your eyes wander. Ding. Okay, so now we have two opponent axes and we have a lightness-darkness axis. We have a three-dimensional color model. Fantastic. So there we are. There's the two chromatic axes we developed. Oh, what's wrong with this one? It's just gray. Well, it's gray because we can't actually display it on this screen. It's outside the range of colors that this screen can display. So that's the gamut of a particular screen, the range of color space that can actually be displayed. And if we have these axes, well, the obvious thing is to consider them to be on an arc, a color wheel. People have been drawing color wheels like this for a few hundred years, but this one is a particularly good one because it's experimentally based. So you have a hue angle, it tells you what the hue is, and how far you are from the gray axis is a thing called chroma. You might have heard of saturation. Chroma is kind of like that, close enough that I won't have to explain the difference in this talk. Okay. So now we have a color gamut. This is the range of colors that can be displayed on a particular screen. And okay, it's in 3 dimensions. There's the lightness axis, and there's the A and B axes. This is pretty tricky to play around with, right? 3 dimensions, especially if you want to compare 2 screens or something like that. How do you do that? It's pretty awkward. So instead of that, we're going to use a thing called a chromaticity diagram. Now, this has some different properties. Firstly, the distance apart of 2 points no longer relates to how different the colors seem. On the other hand, all visible colors fit inside that loop. The loop is the actual colors of the spectrum, the purest colors you can see, starting from like, infrared and whatever, going up through reds, orange, yellow, and so on. And this straight line here, this isn't a color that you get in the spectrum. This is what happens when you mix violet and red together. You get purple. And this also shows you an interesting property. If you have 2 colored lights on this diagram, every color they can produce is on a straight line in between. That's the one useful thing about this diagram. You can predict colors from that diagram. So it has some downsides, but it's 2 dimensions, which is kind of great when you're trying to draw diagrams. All right. Now you know all about color science, or at least all you'll need to know for the rest of this talk. So the prism, what is the prism? Well, let's go back in time to before the web almost, well, when the web was just getting started. There was a new standard for televisions. And instead of being, this is the US standard or this is the European standard, wherever, it was a worldwide standard for high definition television. And it said what the color primaries were, what red, green, and blue actually meant, what measured colors they were. And it also had a white, which is like a normal daylight, D65 it's called. That's like sunlight on a sunny day, reflecting off white paper. That's the color it is. So great, but why would you care? Well, because a couple of years later, there was a proposal called standard RGB. And it uses the same stuff as that TV standard, HDTV, that I mentioned. But it assumes you get some light flickering. I mean, look at this. Look at this. This is supposed to be black. Does it look black? I mean, I can make a shadow on it. It's not black. So there's a certain amount of, we assume that black is actually lifted up a little bit, okay? So that defines what this is supposed to look like. In the early days of the web, you wouldn't even get that. This is, all the colors in the web are supposed to be this. Are they? No. But over time, the monitors you would get moved towards that. The printers that you would get moved towards accepting that and giving a reasonable color. So for a while, that gave us a fairly good system. There it is. That's the 3 colors. And the secondary colors, which lie on the straight lines in between, and the white point there off in the middle. Now you can see it doesn't cover all that much of the visible range, but it's good enough. In particular, it was good enough when you only had 8 bits resolution, because if you had a bigger thing, you'd start to see banding between the individual steps. Excuse me. So there we are. Now you'll be familiar with this, all these different ways you can specify color. You've all used this, hex colors and RGB and names like royal blue and papaya whip and all these stupid names. Let's see what those colors actually look like. There they are. They are all inside that triangle. They have to be because they're all defined in sRGB. So, okay, we can make these colors within this limited range. Is that a problem? Yeah, the world itself has a much wider range of colors than that. And that's where we lived for like 20 years. That's like, this is what we've got. Getting out of it is hard. But meanwhile, other industries were doing different things. The cinemas were moving from shipping around huge big reels of actual film to cinemas to having digital projection. So they needed a standard for this is what my file means when you project it. And so they came out with a thing called the Digital Cinema Initiative P3, Projector 3. I assume there was a Projector 2 and a Projector 1 that didn't work well. But anyway, there we are. So, okay, this is nice. It has a very weird white, by the way. It looks kind of green. It has a red which is right on that spectral locus. It's a very saturated red. It's actually very dim. 48 candelas is very low. But remember, you're watching cinema in pitch darkness, so that's fine, actually. So why would we care about this? Well, oh, there it is, and there's the weird white. So you can comparing the grayed out one is sRGB, so you can see it's a bit bigger. It's not that much bigger, but it's a bit bigger. Well, Ultra HD Premium, a sort of label for what you got to describe your TV as, they required conforming devices to be able to display most of that display P3 color space. So that gave it more prominence in the industry. And other groups followed suit. For HDR high definition TV, you're required to, again, have 90% of display P3. So it was starting to become relevant. But the most important one was from Apple. They took the sRGB standard, swapped out the primaries for the P3 ones, and called the result display P3. And that would have been, yeah, okay, so what? But then all of their new laptops had a display P3 screen. All of their tablets, their iPads, had a display P3 screen. Their watches had a display P3 screen. So suddenly there was this range of capability, and the web was not using it at all. So there it is, as you can see, a bit bigger than sRGB. So there's this wide range of colored screens. You can see lots of colors now. But all those colors I mentioned before, they're still inside the sRGB thing. They haven't got brighter or better. This is actually a good thing, right? If you had a new screen and all your colors were oversaturated, that would be awful. And in fact, if you used Firefox, that's what you got for a number of years, really oversaturated colors. So it's a good thing that the colors we've been specifying for the last 20-odd years stayed the same. But that doesn't help us get this wider range of colors. So this is what the web looks like, kind of drab compared to native. It's like, there's nice colors, but we can't use them. That's web development now. But in the next 2 to 5 years, it won't be. So how do we get out of the prison? We have a new function in CSS called color. And I can say color display P3 and then give it 3 numbers between 0 and 1, okay? Also notice there's no commas, sorry, different syntax. You can also have a slash with an optional alpha component. So there we are. This has been working in Safari since 2016. But nobody cared because it only worked in Safari since 2016. Except now it works in Chrome as well, and in Firefox they're working on it. So this will be good. Also, there's a minimum of 10 bits per component. Remember, you could say RGB parens and then give a percentage, and you could have decimal points in there. It would throw all that away and convert it to 8 bits. Sad but true that they were actually allowed to do that. So we need more range, we need more resolution, so we've got a minimum of 10 bits. And there's that color that I just specified. Oh, it's still in sRGB. Well, I chose that one just to make a point. Of course, you can still specify the old range of colors, otherwise you wouldn't be able to have any pastels or neutrals or whatever. But you can also specify brighter colors. So let's do that. Oh, there's one, display P3 101. What color is that going to be? A green, 0 red, 0 blue, and as much green as you can get. I've got a sort of pink line around that swatch, just to show you that that swatch is not the correct color. This one will not fit on this screen because this isn't a display P3 screen. So I'm going to indicate out of range colors like that. So it's inside the display P3 gamut, but outside sRGB. And that means it will use a thing called gamut mapping, which I'll talk about later, to give you a reasonable approximation automatically of what that color should have been. Oh, here's another one. Look, we've got some negative values. We've got some values greater than 1. I said it's a number between 0 and 1. I lied. Even more, 1.2. Yes, you can actually do that. It will be accepted, it will be stored. So, here are those colors. The green, as you can see, is right on the corner there. It's the brightest green you can get. The blue is outside the gamut of both of those screens, but at least it's still inside this loop, so it's still a visible color. The orange I gave you is actually not a real color. No device ever will be able to produce that color because it would require to be a single wavelength and be more than 100% of that wavelength. No physical device can do that. You can still do math with it. You can still mix that color with another color. But anyway, this is just to illustrate what you can do right now. So we will talk about gamut mapping, I promise, later. These slides are online, by the way. I tweeted out the link last night. All of these links, you can follow them and read more about it. So, predefined color spaces. I already mentioned display P3, but that's not the only one. ProPhoto is a color space that's often used for professional photography. Like if you shoot in RAW and bring it into Adobe products, it will actually be in that color space. And the primaries for that are weird. They're way outside physically realizable primaries, but it's in widespread use, so you can specify it like that. Which means you can use an eyedropper in Photoshop or whatever with one of these photos, get the values, copy them out, use them in your design. There's another one, Rec 2020. That probably doesn't mean much to you, but it's the latest TV standard for 4K and 8K TVs. So a lot of content, like if you watch Netflix, for example, the color values are in that color space. So again, if you're trying to match to some video content, you can just take the values straight out and use them. OKLCH, what's that? Well, it's a very new thing. We were somewhat hesitant to adopt it into CSS, but it's very good, so we did. L is the lightness on a 0 to 1 scale. C is the chroma, I explained, that's how far from the neutral axis. And then the last one is the hue, an angle, 0 to 360. So you can specify it like that. Think of it as like HSL, except it's so much better. Because in HSL, if you pick two colors like 30 degrees apart, they might look really different, or they might look almost the same. You've got no idea. Whereas OKLCH is vastly better. The distance apart in angle of two colors tells you how far apart they actually look. I have a link here to a color space converter that Leah and I wrote. It's a JavaScript library that converts from one color space to another. So if you have a color in one thing and you want it in a different thing, it will do that conversion for you. All right, so this is all very well and good, but obviously you can't just throw this at your users and hope that it works. So there's a few media queries you can use. First one is to check if there is a wide gamut screen available. So the keyword for that is P3. And then you can use the color because you know it can be displayed. And if it doesn't work, you could give a fallback color, which is your choice of what you want displayed instead. And you can also use good old so everyone uses @supports already, right? For all sorts of stuff. You use it to test whether what you're about to do is actually going to work. Well, you can use it here. So I've set the background to this display P3 color. And then if that works, okay, fine. I'll set my actual color to what I want. You can also use this CSS syntax in Canvas. If you set up a canvas with a 2D context, you can ask for, you see this color space thing? You can ask for a display P3 canvas. Canvas never used to say what color space it was in, by the way. It was just, it will set up a 2D context. They've changed that now. If you don't specify it, it's sRGB, which is what it always was, really. And if you do, you can say it's a P3 instead. And then you give in backticks the actual syntax there, like from CSS, and you can draw and stroke and make graphics using that. All right, so now we can specify colors that are bright and vibrant and like the same colors you would get in a native application. What else can you do? Well, you can mix colors. excuse me. You can mix two colors. Firstly, you say what color space you want. OKLab is probably the best one. It's the A and B axes that I showed you at the beginning of the talk. And then you give any two colors and a percentage. You can give two percentages, but why would you bother? Because they add to 100%, so just give one. And that will mix them. Okay, so let's do the working now. So the teal, notice that I specified it as sRGB, but it all gets converted to the working color space. So that one gets converted like this, olive gets converted like this, and then you just interpolate these two numbers by the percentage you wanted to give the result, and then it gets converted to whatever you need for display. I'm sorry about the coughing. I got a cold on the way over here, adding to my other worries. So, as I said, the colors to be mixed can be in any color space. You don't have to convert them. That will happen for you. They're converted, they're mixed by the percentage, and the result is in the mixing color space. So the result may be out of gamut. It's very easy to mix two colors which end up being out of gamut for your device. But that's okay because we have automatic gamut correction for that. So here is an example. If you look at this slide, you'll see the JavaScript which actually does all this, because obviously the browser doesn't know how to do it yet. Oh, thank you. So you can change to a different color space, and you can change the colors, and you'll see the worked result. So I do recommend downloading these slides because there's lots of links, and you'll be able to play with the actual implementation even before the browsers get around to implementing it. Go away, okay. So gradients. Gradients also, so far they've been mixed in sRGB. This turns out to be a really bad choice for color mixing because the signals are gamma encoded and they ought to be mixed in linear light, and they're not. All right, so here is two colors, a red and a green. And I've mixed them in LAB, and as you can see, it goes through the expected range of colors. Like it goes to orange, and then yellow, green, and then green. Here's what you get now. If you do that gradient, it goes all dark and muddy in the middle. It's kind of horrible. This is what you're using now. Of course, what you do is you put extra stops in, right, to make it look right. You shouldn't have to do that anymore. You'll get a reasonable result. And this is OKLab, which here is much the same. This thing, CIE Lab, it's been around since like the 1970s. It's widely used. It has some problems though, which we noticed, which is why we don't really recommend it. We recommend OKLab instead. Let me show you a problem. So this is a mix between white and blue. And in the middle, we've got purple that we didn't ask for because there's a limitation of the color model. The hue linearity is not good in the blue region. You get this weird purpling effect. There is an sRGB, better, but still actually a bit purple and also a bit too dark in the middle. And there's OKLab giving you a nice smooth transition, nothing unexpected. That color just fades out to white. So how do you get that? Well, there's a regular gradient, right? You just give the two colors that you want it to make a gradient. And if you add in OKLab, yeah, I'm so sorry about the coughing. I know it's annoying. So you just say which color space you want to interpolate in, and your gradient will do that. You can also mix in a polar color space with an angle and a chroma. And if you do that, there's two ways around the circle, right? If you've got a color here and a color here, so you can say the shorter way or the longer way. All right, so far we've mixed colors, we've specified colors. We can modify colors as well. You can define a color, and I've done it as a variable here because this is where this really shines. If you've got color variables coming in and then you combine them in various ways. And now I can take the individual components of that. I've got the lightness, I want it just the same, but I'm using a calc expression there to bring down the chroma, make it a bit less saturated, and I'm shifting the hue by 120 degrees. And you have these predefined variables. So if you're working in LCH, you'll have L and C and H, which you can use in a calc. They're predefined for you. If you're using an XYZ model, then you've got X, Y, and Z. And if you're using an RGB-based model, then you've got R, G, and B that you can mix with. This looks quite useful, but for RGB it's less useful because these values are gamma encoded, and that means you're not going to get the results you really want. But it does mean that you can basically craft your own. You can go crazy with calc. You can set variables to it and then get them from JavaScript and mix with them, pop them back. There's all sorts of stuff you can do. Gamut mapping. I did say I would talk about this. So these colors have to be modified, and the good news is they get modified by the browser, not by you. You don't have to do that work. What we want is a color that looks similar, but it's actually displayable. So here's an example. This is a top-down view of the OKLab color space. And I start with this purple color. The dashed line is the gamut of the display that I'm using. So this is in gamut, this is fine. But as I change the hue angle, I get to that one over there, which is out of gamut. It can't be displayed. So I need to bring it in towards the neutral axis until I get a less saturated color, but of the same hue. So that's what gamut mapping will do for you. And it's called constant hue chroma reduction. That's the technical name for it. Because changes in hue are really noticeable. They're really awkward. If you change the lightness a bit, it's too light, too dark, it's less noticeable. If you reduce the saturation, reduce the chroma, you're recognizing it as the same color. Okay, now I have a link there. I did a whole other extra talk about just this one subject. So if you're really super curious, you can watch that, and I'll explain why we did what we did in CSS. But here's an example. Now this is a slice through a color gamut. On the left-hand side, we've got lightness, and out here we've got chroma, and this is our starting color, which is outside the boundary. So we basically bisect that line. Okay, we're inside, so we bisect again, and keep going until we get close to this boundary. And once it's close to that, it just gets clipped. Here's an example again. As I said, CIE LCH has this problem of purples. Here's the sRGB blue, and as we go out towards the neutral axis, it definitely turns purple. It's really ugly. Here is OKLab, which has a different shape, and you can see that the hue stays constant across the whole thing. That's why we're doing gamut reduction in this OKLCH color space. All right, so the big question, can I use any of this stuff? Well, no, but nearly. Basically, we're waiting for Firefox. Safari has had this in technical previews, and then in like Safari 15.2 onwards, you can use all of these things. Chrome, in the last 2 months, has suddenly gone from, yeah, we're looking at it, to here it all is. Between like Chrome 107 and 110, they implemented most of it. And you get that in Edge as well, but with a bit of a delay. And Firefox, well, they've done color mix, but only for sRGB inputs. They're talking about how to add the other stuff. The thing is, the object model has to change, right? At the moment, if you look at a color in the object model, you'll have basically a 32-bit number with red, green, blue, and alpha. And they have to change all of that so you actually get 4 floats instead. So it takes them a while, but they are working on it. I know the people who are working on it. Soon, you will be able to do this. And why do I say it's soon? Because there's this thing, Interop 2022. The browser guys all got together at the beginning of this year and decided 10 groups of CSS features on the web that they were all going to work on together. They all promised they wanted to increase interoperability. It also had to be things that had tests, and this is the percentages of those tests that they pass. And they put this up on a public tracker so you could look at it, you could see how it changed week to week, you could see which tests, and one of them, the second one down, there's like 10 focus areas, but color spaces and functions, that's all the things I've been talking about today. That was on their interop push. So, well, you can see 98%, 97%, and then Firefox at 54. But this will continue on to next year where they will all be pushing to get to 100%. So, I have confidence. This stuff you will be able to use soon. Ish. Mail your Firefox guys and say, hey, I wish I could use this, but you guys are being slow. They know. It's just a case of, they prioritize what people whine about, so whine lots. All right, how are we doing for time? Do we have enough time for me to do another 5 minutes on HDR, or should I skip it? Someone who's in charge, tell me. Are we good? We have 5 minutes. Do you guys in the audience want to hear 5 minutes about high dynamic range, or are you really kind of bored? Thumbs up? Thumbs? Yes, all right, let's do it. Okay. High dynamic range. So I mentioned the 8 bits restriction. Here's a typical scene, right? We've got a sunset, which is very, very bright, difficult to look at. We've got some mid-range tones, and then we've got, theoretically, all the shadow detail on the back of this chair, which you can't see, it's just solid black. So the real world has a much wider range of lightness and darkness, and our eyes can see a lot of that simultaneously, so the next push is to be able to express that as well. So consumer stuff is using this. I mentioned 2020, 2100 is the HDR version of it. But gaming consoles now, if you get a gaming console, it will have high dynamic range. Your games will have that range. The TVs will have that. If you bought a TV in the last 5 years, it will have high dynamic range. And the laptops and whatever, Apple ones, but also, the Dell I was using, they all have HDR either coming or partly implemented or implemented. So the hardware is getting there. And also there's a new image format called AVIF, which is basically a single frame HDR video. So it can display all that dynamic range, as well as the wide color gamut as well. So it's a good choice, actually. So a high dynamic range implies also ultra-wide gamut. So there's a standard, Rec 2020, so CSS already supports that. And there it is. Look how much bigger it is. The red, there are very few devices that can display all of this, but there's a lot of devices that can display most. And you can see it's a big increase on sRGB. In particular, the blue is right out on the spectrum there, red is right out on the spectrum, green is poking out away there. So it definitely is a noticeable increase in the range of colors. If you see like a Netflix or a Amazon Prime or one of those videos, the content is actually mastered in P3, or a little bit bigger than P3. But then it's actually rendered out to Rec 2020, and the reason for that is HDMI cables can either display sRGB or they can display Rec 2020, but that's your two choices. So they have to kind of convert it to get it along the cable physically. So that 2100 is the HDR version. So it has two different encodings, which I'm going to talk to you about. First one is hybrid log gamma, developed by the BBC and NKK in Japan. It uses 3/4 of the code space for your normal range signal and the rest for highlights. And it's defined so that a normal white is at 75%. So if you're watching something and in a bright room, like a sports bar or something, they can just take the whole brightness range up. So the summary, I mean, it's quite a complicated spec, but the summary is hybrid log gamma gives you brighter displays so you can cope with brighter environments. It seems to me much more suitable for use on the web because we consume web content in a huge range from right in the dark to broad daylight, and we need to be able to see it in all of those circumstances. The other one is PQ, perceptual quantizer. This is what Netflix and whatever use. It's aimed at viewing HDR content in a dark room. That's really what it's good for. It has much more highlight capability, but if you change to a different viewing environment, everything has to be recomputed, which is complicated and not well described in the spec. So in practice, you'll meet both these types of content, and they have different strengths and weaknesses. There is a proposal now to add HDR to the HTML canvas. We've already added two things. Firstly, the wide color gamut stuff. Secondly, something so you can use half floats instead of 8-bit components. So the next thing is to add HDR to it. This is being implemented now. In Chrome, if you use the experimental features flag, you can play with that. You can also do things like query the dynamic range headroom. You can query the screen gamut. So this looks like being quite a useful technique for CSS as well. You set up a little canvas somewhere, you query its properties, you know more about the screen. Now you've got more confidence in the colors you're going to use. And yeah, as I said, it goes beyond 8 bits, so we've got float. And that's it. These slides are online at that URL. That's my email. I'm at svjesus on Twitter, and I'm at svjesus at mastodon.social as well, which I should put on this slide, really. Okay, I hope that was interesting and useful. Thanks very much. Feel free to tweet questions at me, and I will try to respond to them. We're done.